Okay. So should I start?
Yes, please.
So welcome. So today it's the fourth lecture of this program about axions as dark matter candidates, and now it's the first time that I really talk about axions as dark matter. So there was a lot to be prepared until now, and it came also a surprise to the in a sense to the original proposals of the axion, that even an invisible axion could be indirectly visible or make problems. At the beginning, they thought it makes problems as because it may possibly lead to much dark matter, to too much dark matter, and so this came as a surprise, and it's also a bit it's surprising that an axion which is very light can be a dark matter candidate. So, but we will learn how this works in this course. So first, just because we can get now to the dark matter, I want just to remind on the big success of the standard model of particle physics, that we have this very beautiful model which describes the interactions of all known particles. There's of course, so I mean, there's three families, and there's some things are maybe too much to describe just our everyday life, but it's a very nice and very economic model which describes all the interactions we know of all known particles, and also with a very remarkable accuracy. So as we learn from our collider experiments, and also not only from the LHC but also from the B physics, Bell, and so on. So this is really a remarkable success. However, so there's a big flaw. So as soon as we look outside of the Earth, so to say, if we look into the universe, we learn that the standard model accounts only for a few percent of the total energy of the universe. So astronomical observations on the galactic size. So for example, here this gives the velocities as a function of distance in the Milky Way, for example. And on cluster sizes with weak lensing, or even on the largest sizes with the cosmic microwave background, they all indicate that 85% of the matter in the universe is not comprised of the ordinary matter. So the ordinary matter makes only about 5%, and 85% of the matter, 5% of the whole budget, and yeah. So this is really, and 85% of the matter is not comprised of ordinary matter. Now, theoretical particle physicists, they are, of course, very imaginative, and they have proposed a plenitude of dark matter candidates. So here are only such, so there are some think about the supersymmetric extension of the standard model. In the minimal supersymmetric standard model, a neutralino could be a dark matter candidate, or a gravitino. Then these belong to the generic class of weakly interacting massive particles, WIMPs, and there is people who think about so to say the dark hidden sectors for dark electrons and dark neutrons and such things. So there are lots of proposals. And these proposals or these candidates, they span a huge range in masses and in the interaction strengths. So the WIMPs and in particular the neutralinos, they are supposed to be have masses in the multi-GeV to 100G or even TeV range, with interaction cross sections of typical weak interactions. then but the gravitino would be much could be lighter and much weaker interactions, and so on. So there are many. There are even these Wimpzillas, which would have really huge masses and a wide range of interaction cross sections. And the Axion, as I said, is very light and also very weakly interacting. And it's even more weakly interacting as the lighter it is. So here, of course, now in this course, I concentrate on QCD axions. And these QCD axions, they belong, according to this nice US Cosmic Visions white paper, to the generic class of ultralight dark matter. So we will learn why and how the QCD axion lives in this parameter range. It can be even extended to even smaller masses, as I said already later, but it cannot be as a dark matter candidate and so on. It cannot be extended in this direction, but it could be even go to even smaller masses. And so now then let's go into these measures. So how we are supposing that axion are produced in the early universe. So how is axion dark matter produced in the early universe? This is the production is going via the so-called vacuum misalignment mechanism. Now, first of all, the axion comes into the play where after the breaking of the spontaneous breaking of the Pechegwin symmetry. It may be restored at very high temperatures, but as soon as one goes below the high temperature, or maybe also during the inflation, this Pechegwin phase transition takes place, and then afterwards the axion is there as an agent, so to say. Now this axion field evolves then. So first of all, this axion field. So we have this early universe. Plasma and so on, but the axion takes random initial values in causally connected domains in this cosmological fluid. And the typical size of a causally connected domain is given by the inverse Hubble parameter. So to say at this. So this is because the Hubble parameter or the Hubble expansion rate is growing. The size of these domains changes, but it can have an initial value just and can have different values in different causally connected domain. Just this will be attained randomly. So we can now consider, and now we have to consider how does the axion field evolve in one of these causally connected domains. Now this is described. The evolution of the axion field is described essentially by the Klein-Gordon equation in this expanding universe, and apart from the boundary effects, so it's more or less homogeneous this field inside this Hubble connected regions, and there it evolves, so to say, like a damped harmonic oscillator. So why is it? It's nearly harmonic oscillator because the potential at high temperatures, the axion potential is really given by a cosine of theta. So this is this periodic potential is just the cosine, and then if you differentiate or minus the cosine, if you differentiate it, then you get a sine. So and for for small thetas, for small theta away from the minimum, for small initial values of theta, this is essentially the potential of a harmonic oscillator. Yeah. Therefore, and the damping you get because of the Hubble expansion. And if the Hubble expansion rate is much larger than the temperature, then this term dominates, and so to say the evolution of the field is frozen. So then you are stuck with the initial value of this field as long as the Hubble expansion rate is larger than the mass of the axion. Now I've emphasized here that the axion has, of course, a mass at zero temperature, but at high temperature the axion mass changes. This is because we had before, so the axion mass is generically given by the square root of the topological susceptibility divided by FA, and only at very low temperature we can calculate the topological susceptibility in terms of the pion mass and of the pion decay constant. And we saw the formulas before, but at high temperatures, at temperatures above, the QCD crossover from the hadronic phase to the quark-gluon phase, this topological susceptibility drops. So it drops and it gets smaller. It drops like an exponent. The exponent is essentially the temperature to the -7th plus a number of quark flavors, active quark flavors. One can derive this from the instanton gas approximation of the vacuum at high temperatures. But as I will show that this is also, so one can also now meanwhile also lattice results on this quantity. So the axion mass at very high temperatures is essentially zero, and the axion initial value is or the axion field is, so to say, fixed or frozen at this initial value. And then as soon as the Hubble expansion rate drops below the mass, I mean, the Hubble expansion rate, of course, at the beginning, the universe is expanding very faster, and then the expansion goes lower and slower. And at some time, it falls below the mass of the axion. And then the axion starts to oscillate in this potential, in this axion potential. So, and then it oscillates around the minimum of this potential. So, but you can see it here. So here's an illustration of the evolution of the axion. As I said, so what is shown here is the axion field. So A over Fa. So essentially the axion angular field versus 1 over the temperature. So the time goes in this direction, so to say, because the temperature of the universe is falling. So the time proceeds along this direction, or this is the direction of falling temperature. So at high, and what is plotted here and below is essentially, this is the axion mass as a function of the temperature, and the Hubble expansion rate as a function of the temperature. So, and then you really see, so as long as the Hubble expansion rate is larger than the axion mass, the initial value, the axion field is frozen to its initial value, and then as soon as soon as the axion mass is larger, or as soon as the expansion rate drops below the axion mass, then the axion field starts to oscillate around 0. And of course, these are damped oscillations also still because the universe is still expanding and so on. However, the Axion number per moving volume, when you calculate this is growing. So here is essentially no Axion produced. And then this starts to oscillate around a non-zero value, and this is very high, so to say, per co-moving volume. Here are 10 to the 12 axions, so to say. So this depends, of course, also on the mass. So there are two things now. So the equation of state is in fact the one. So you have to calculate then the pressure of the Axion fluid divided by the energy density of the Axion fluid, and this is about 0. So this is exactly the equation of state as cold dark matter, and in fact, so this is also supported by the fact that this kind of coherent and spatially uniform oscillation of the Axion field corresponds indeed to a coherent state of non-relativistic Axion particles. So it's really, it's a non-relativistic Axion particles, but sometimes, and also later for this Axion dark matter experiment, it's better, so to say, so many effects and are better understood in the wave picture rather than in the particle picture, so to say. And this is because we have really, there are many particles inside these coherent states, so to say. Now, to make this a bit, so in these times, in 2009 and so on, so one was still doing these calculations. For example, for the Hubble expansion rate, one had to use one had still quite some uncertainties in the equation of state parameters, which are entering into this game to determine the Hubble expansion rate. So if in the effective numbers of effective entropy and energy and heat capacity, degrees of freedom, and also one had also still some uncertainty in the topological sustainability as a function of temperature, or in the Axion mass as a function of temperature, which is not shown here in these lines. So, for example, here they used for the Axion mass, they used the instanton gas approximation, and here they used some interpolating fields, interpolating expressions for this what would you say, this effective degrees of freedom and so on. Nowadays we have very good input from lattice QCD, for example, on the equation of state, or on these functions. So G rho is the effective degrees of freedom for the entropy, for the energy density. GS is the effective degrees of freedom of the entropy density, and GC of the I don't know. No, I forgot, heat capacity. Yeah, okay. And you see, so as a function of temperature, this has been determined by on the lattice. So one is really observing here the transition in a sense from a hadron gas into through the phase to the QCD crossover to the quark gluon plasma, which is of course still, even at these high temperatures, is still not a perfect gas, so to say, in which all the, or ideal gas where all these functions should be all the same. And moreover, also for the topological sustainability, has been determined. So this is topological stability as a function of the temperature. And as I said, so here is this value which in fact agrees with the expression which you get from perturbation theory. It is that it should be the square root of chi should be m pi times f pi and reduce quark mass factors. So and if the temperature exceeds a few hundred MeV and is above the QCD crossover, then you get a power law decay of the topological susceptibility, which means that the axion mass, which is proportional to the square root of it, it will be also falling down power-like. And the power is reproduced by the dilute instanton gas approximation. Now, okay, so you have these inputs, you have this equation, and this equation can be solved, and then you get a prediction for the axion dark for the axion dark matter abundance. One has now to discriminate between two important cases. So let us first discuss the Preinflationary Pidgeck-Winn spontaneous symmetry breaking scenario. So nowadays we are believing that that in the very early universe there was that the hot radiation dominated era was preceded by an inflationary era where the universe was exponentially expanding, and only after this exponentially expanding, the universe reheats, and the energy is given from the so-called inflaton field transferred into the radiation of the standard model, and maybe on the standard model particles, yeah, okay. Now, so if the spontaneous symmetry is broken before or during inflation, which means essentially if this Pidgeck-Winn symmetry breaking scale or this axion decay constant, let us say this, it's more clear that the axion decay constant is larger than the Hubble parameter during inflation divided by 2 pi. This is essentially the Hawking temperature of this de Sitter phase. And if it's not restored afterwards, after reheating, then the axion dark matter density depends on the initial value of the axion field in the patch, which becomes later the observable universe. So as I said, I mean, here the universe during inflation still consists of so to say causally disconnected patches, and each patch the axion takes a field takes a certain initial value. But now, if there is nothing, if the Pidgeck-Winn symmetry is broken during inflation, and if it's not restored afterwards, then then so to say this small region becomes the whole observable universe, and therefore in the whole observable universe, this axion field had the same initial value. Now, and then of course, then so to say, our whole universe, this initial value was fixed, so to say. So then, therefore, then if we calculate then the dark matter abundance, the axion dark matter, cold dark matter abundance today, then this will depend on the value of this on this initial value of the Axion field. So this is an environmental parameter. So and theta, because it's an angle, theta can be between minus pi and pi, or this can be between is of the order, can be between 0 and pi squared, so to say. This value here in this theta squared. So in addition, of course, it will depend on the Axion decay constant, because in a sense the Axion decay constant gives, so to say, determines also how much energy, how much energy density of was in the initial potential, because this is of course theta I over Fa, but in this the energy density will be proportional to theta I squared Fa squared. So and therefore the higher the higher Fa, the higher the number density. So but it's not going with F squared, because there's this temperature dependence and which diminishes this somehow. It's not really 2, but it's just 1.1. But still, so this means now, but we can understand the higher the decay constant, or the smaller the mass, the more dark matter you have. So this means and in principle, yeah, you can then determine from this behavior, or if you do it really numerically, you have to take into account that it's not really a harmonic potential, but it was a sinusoidal potential. So if you take all this account, then you get these curves. So if you want to have 100% of the dark matter in axions, then the parameters here, this theta I, or here it was called theta 0, and MA or FA, so you can always translate these two quantities into each other, have to lie on this line. So if you say, I don't want to have a fine tuning in this theta I, so theta I should be of the order of 1. Then you need, in order to have 100% of the dark matter, you need an angle. You need a mass of the order of micro electron volt, or an Fa of the order of 10 to the 12 GeV. But if I say, okay, I think axions are so the decay constant should be of the order of the grand unification scale, then you read off here 10 to the 17. Then you see you need an initial angle of the order of 10 to the -3. So it's not a terrible fine tuning to get the 100% of the dark matter. So, but it's something of 10 to the -3, and then you can get 100% of the dark matter. And then, of course, I mean here, so in this direction, Fa is growing. So here in this region, you would have an overdensity of dark matter, and here below you have an underdensity of dark matter. So this above is not good. But yeah. Okay, so this was the so-called pre-inflationary pitching wind symmetry breaking scenario. So in principle, for any value of the decay constant, I can find an initial value which explains 100% of the dark matter to be made of axions. So it's not really, so you see, so this itself, it's not a, here you don't have a miracle, so to say. It's not like in the WIMPs, with the WIMPs, you had the WIMP miracle. So you get from this thermal production mechanism, you get 100% of dark matter if these massive particles have a weakly interacting cross section. And here, but here it's not. So here it's more like I was talking with Frank Wilczek about that, but he said it's an Axion revelation instead of a miracle, because he said you look, so as soon so we have the limits, we have so to say the astrophysical limits from which say that this decay constant should be larger than 10 to the 9 or 10 to the 10 GeV. And we find, and now the Axion revelation is this is exactly the boundary where one can start to have Axion to be the 100% of the cold dark matter. So it's a revelation rather than a miracle. So now, but now let us go to this post-inflationary Pechik-Wind symmetry scenario. In this case, one gets a lower bound of the Axion mass in order to avoid the overdensity. What is the reason for that? Now, if this Pechik-Wind symmetry is broken after inflation, then as is illustrated here, so this Axion takes also even today will take on or took different values in different patches of the present universe. So it was not like there was one of these patches was inflated to the whole universe, but because inflation was already taking place before, and then the Pechik-Wind symmetry was restored somehow, and then it's again broken, so to say, at some scale, and then we get this different values in different patches in the present universe. And so in order to now we have to average over the random initial Axion field values, and then of course we never never get to these very smallest values, and therefore, so if we do this average, then we find that that from this misalignment mechanism, if this misalignment mechanism is working alone, then we get 100% of the dark matter, namely the dark matter fractional energy contribution to the energy density of the universe is making up 0.12. So we see that that the Axion would be fixed to 30 around 30 micro electron volt by this mechanism. As we will discuss very short now, that in this scenario, in the post-inflationary Pechik-Wind symmetry scenario, there are further contributions to the Axion cold dark matter density, and therefore this is only a lower bound, so to say, and this provides only a lower bound. So there can if this the misalignment production makes only a part, makes only a half or a third of the whole energy density contribution of cold dark matter, then the mass could be higher, of course. So so to conclude this page, so this observed cold dark matter abundance is really putting a lower bound on the Axion mass, and if one can make this a bit more concrete and so on, and so this is the lower bound on the Axion mass is 28 with an error of 2 in the last digit, so it could be 26 still, so micro electron volt. So in this post-inflationary scenario, there is really a lower bound on the Axion mass. And this was, of course, important for Axion experiments, Now, at the moment, we don't know whether the pedagogical symmetry is broken before or after inflation, but if one is doing experiments at small masses, one will definitely not get an observation if the post-inflationary pedagogical symmetry scenario is realized in nature. Now, as I said, there are even more axions expected in this post-inflationary pedagogical symmetry breaking scenario. Why is that? So I again go back to this picture or this illustration of the post-inflationary scenarios. So as I said, there are random initial values in patches of the size of the conduct after the pedagogical phase transition. So so there are these red dots, and now if we go now with a magnification glass into these red dots, what they are meaning, what their meaning is that at some of these dots, so to say, if you go around these regions, you are increasing, so to say, the value continuously from 0 over pi half pi 3 pi over half again to 0, which means that you go somehow these initial values are somewhere going around the whole thing, and this means that you encounter here something like a singularity, and this singularity is essentially the center of a cosmic string of a one-dimensional object, which goes through such lines. And so automatically by this kind of, in this kind of phase transition, where this is a phase transition of a global U1, of a global U1 theory, you get automatically a network of cosmic strings generated by this kind of, this is called the Kibble mechanism. If you have these causal regions and you have these things, then you get this singular, this kind of topological defects. Sometimes they are called topological defects, and this is a one-dimensional topological defect. This is a string. So this network of cosmic strings, they are generated by the Kibble mechanism. They are also generated by the Kibble mechanism in the pre-inflationary scenario, but in the pre-inflationary scenario, so to say, you expect then after inflation only one cosmic string in the whole observable universe. But rather in this case, during the evolution of this, you still have all the time, you have still cosmic strings, and about one cosmic string per causally connected Hubble volume, so to say. But you have them. You cannot. You have more patches, and therefore you have still a network of cosmic strings for a long time. Now, and there is even more to it. Around the QCD phase transition, really the axion potential develops, and if you have like in the DFSZ axion model, which I was introducing yesterday, if you have a non-zero domain wall number such that the axion decay constant is not just the Peccei-Quinn symmetry breaking scale, but it's in fact the Peccei symmetry breaking scale divided by this domain wall number, then actually the axion potential looks like that. And depending on n, has several minima or maxima inside the range, fundamental range of this axion from minus pi v Peccei-Quinn to plus pi v Peccei-Quinn. And what this means is that to each cosmic strings, there are n domain wall number attached to a string. So for example, this is an example for domain wall number 3. To each cosmic string, there are 3 domain walls attached. So you have even two-dimensional topological effects as soon as the domain wall number is larger than 1. So in the KSVZ model, domain wall number typically is 1, and so then there are no domain walls, but in this case there can be domain walls. And now in both cases, so I now should first say, so for the domain wall number 1, this string wall system decays after the time, and so to say these string, so there remain just so to say walls, and these walls they disappear. So they are short-lived. They are these domain walls. And in the case of domain wall number larger than 1, these string wall systems, they are long-lived. So they can they can, if they are living too long, then there is a domain wall number problem, because they would overclose the universe. So there should be some extra violation of the Pidgeck-Winn of the global symmetry, in order that those disappears. But such extra violations are expected in any case, because there is a conjecture that there are never exact global symmetries in the theory because of quantum gravity. Now, okay, so in the course of the evolution of such networks of strings and domain walls, there are axions produced all the way during this evolution. So when these networks so these strings interact with each other and so on, and there are axions produced, and they add to the axions produced by the misalignment mechanism. And this is quite a complicated problem, has to be treated with lattice simulations. And the amount of axions which is coming out from such collapse of networks of strings and domain walls is currently still under debate. There are many people, many groups are working on that. So I have here listed a number of papers on that. And so at the moment, one can say that the required axion mass to explain 100% of the cold dark matter abundance in the post-inflationary Pidgeck-Winn symmetry scenario is still quite large. So if the domain wall number equal to 1, then the axion mass should be between 26 microelectron volt. This is, so to say, so some of this investigation, they found that the contribution is negligible from the topology, from the decay of or collapse of the network of strings and domain walls is negligible, and others they found that it's very, very large, and therefore so the range is still going from 26 microelectron volt to 0.5 millielectron volt, while for the domain wall number larger than 1, the lower bound, so the contribution is always quite strong, and therefore you start, so to say, just above this limit, but then this upper limit is already so excluded by some astrophysical bounds, essentially the bounds from neutron stars and supernova 1987A, which allows maybe 60 millielectron volt, but not 130. So axion dark matter, or the dark matter axion mass spans really a huge range. It in the misalignment mechanism, in the Preinflationary, it can really go down to very low masses. And if you look in the region where you don't tune at all the parameter, then it's in the microvolt range up to 100 micro electron volt, and above you have to tune again this initial angle near to pi. If you have the post-inflationary scenario, you have this lower bound of 26 micro electron volt, but it can still be in a quite large range of masses. And if you have these long-lived domain walls, for example, the DFSZ models, the masses could be even higher, or is higher. There are alternative or newly proposed Axion production mechanism which require another initial conditions which are sometimes fulfilled. Also in our ZN Axion model, one gets automatically such a so-called kinetic misalignment mechanism. In this case, the Axion mass again is in the higher, the required Axion mass is again in the higher mass region. Okay, so I think I stop here now for a few minutes. And you may now ask questions about this Axion dark matter.
Yes, please. So from the students, any question? There was a lot of things. Yes, Kamil.
Hello.
Hello.
I have a question. Have you thought about interaction between the Axion dark matter and the CMB cosmic microwave background?
Yes.
So
there are limits, but also from the CMB microwave background, not on this Axion cold dark matter, because it behaves exactly as the cold dark matter, which is always described in the CMB. But there's there can be another component of Axion dark matter, namely Axion hot dark matter, which can be in this post-inflationary scenario. Of course, there can also in the early universe, one can also produce thermal axions by scattering processes with gluons, by this gluon processes and so on. And this will be a radiation background of axions, which you can then translate into an effective number of neutrinos. And this has been considered, yes.
I was thinking rather about this axion and two-photon coupling.
Yes, but there in this early universe, I mean, there are also, of course, considerations of axion photon oscillations with the CMB and so on. But this is all there have been these investigations, but typically these were always relevant for axions for axion-like particles, but not for the QCD axion. Because the QCD axion, because these interactions were always relevant for axions which had a mass much smaller than the QCD axion.
I think when you want.
Yes. So I can continue. So I start now with Axion experiments. So I first concentrate, of course, because this is a lecture about axions as dark matter candidates. So I start with Axion dark matter detection. And not with the other experiments, which are purely laboratory experiments. So so the first proposal on how to directly detect Axion dark matter was in a seminal paper by Pierre Sikivi in '83, where he proposed the following. So he said, because of this two photon of this E dot B interaction of the axion, if you have an axion dark matter wave, so to say, yeah, then this may convert into an electromagnetic wave, or into a photon, if this happens inside a magnetic field. So you suppose you have here a coil, and you have a magnetic field in this direction, and if an axion and this magnetic field region, or this vessel is flying through the halo, dark matter halo in the Milky Way, then the axion can convert into a photon, and this photon can be detected. Now, so in order to enhance this detection probability, or to enhance the signal, Pierre suggested to put this this whole system, or to put into this magnet a microwave cavity. Why a microwave cavity? So in a microwave cavity, you have fundamental modes, so to say. You have certain modes, and if you can excite the fundamental mode of this cavity, and if this cavity has a very high quality factor, then you can enhance the power output of this signal by a huge amount. And in fact, so because axion cold dark matter axion, if it's cold, so then it has nearly only a very low velocity, namely the order of the velocity of the axion is of the order of the velocity dispersion in the Milky Way, which is of order of 10 to the minus 3. So of the velocity of light, and therefore, so the velocity dispersion is 10 to the minus 6. So so you expect, so to say, that this electromagnetic wave, or this single real photon, has a frequency of the equal to the mass of the axion, and the width of the signal is given by the relative width is of the order of 10 to the minus 6, because it's 10 to the minus 3 squared, so to say. And so if this cavity has a resonance frequency, now say at a gigahertz, then you are most sensitive to an axion which has 2 pi times the frequency, which would be in this case 4 microelectron volt. So for a microwave, to detect a microwave electron, a microelectron volt mass axion, you need a cavity which has a resonance frequency at around a gigahertz. And the power output will then be given by G squared, this coupling squared, times the magnetic field strength squared, times the energy density in dark matter, times the volume of this cavity, times the Q factor. So this resonance enhancement divided by MA. Now, of course, now the problem with this method, so this method is very sensitive. If you know, and you could very quickly determine the axion mass if you know the axion mass. But however, as I said, only in very exceptional cases we have models which predict the axion mass, because it's so the Petric-Wien symmetry Px is a new parameter, so it's not predicted at all, and therefore one has to scan a range of axion masses, and this is the cumbersome part of this kind of detection scheme. So the detection scheme is very sensitive, but you have to optimize that you can scan, so to say, in small steps, and the steps, the size of the steps is determined by this velocity dispersion. So it should be relative is so to say in steps of 10 to the minus 6 in the relative relative bandwidth, so to say. So this is the reason why it takes quite long, and why there are now many experiments. So at the moment currently running, there are a number of experiments. So there is ADMX. They were the first, and they are the most experienced. So they are working already since many years on that, and they have also, so to say, they have dig the deepest in the parameter space. They have reached sensitivities below the DFSZ model. Then there is CAP. This is the Center of Axion and Precision Physics in South Korea, who are working now, and they are now also starting to dig deep into the parameter space, starting at higher masses, or starting at frequency between 1 and 8 gigahertz. They want to scan this region first. So somehow ADMX, they started these lower energies and lower frequencies and going up, and CAP starts at a bit higher, and then they are going up. Then there's Haystack, which is active, and Organ. Where's Organ? Here's Organ, and Quarks A gamma, and RADES at CERN. So there are a number of experiments at this RBF. These were old experiments which are no more active yet. So these were the four, so to say, the first generation of these cavity experiments before ADMX came into play. Now, as I said, so it takes some time, and then at the highest frequencies, it gets more and more complicated, because you have because the resonance frequency is of course determined by the inverse of the size of the cavity, and therefore if you go to higher, if you want to go to higher masses, that means to higher resonance frequencies, the resonant cavity gets smaller and smaller. So you have to either make constructions with several cavities working together, or so there are different ways on the cavity on this cavity development for dark matter searches, where they try to go to higher and higher frequencies. There are so-called pizza cavities and all kinds of things. So that's quite interesting. However, it's so one can summarize this. These microwave cavities, they are really reaching deep into the axion band. So they are really going. So this line is this DFSZ line. So they are trying deep in the axion band, ADMX is so this is the forecasted or projected sensitivity of ADMX, then the one of CAP, and so on. And they will, so to say, in a sense, they will scan the whole region between microelectron volt somehow, maybe not really microelectron, but maybe 2 microelectron volt up to 100 microelectron volt. So there's also this. So in Italy, this clash, and recently it was renamed in flash because they wanted to use another magnet. This is also a cavity approach. These are reusing big magnets from previous accelerator experiments, and so this will enlarge a bit. So maybe one should say here, it's really going from maybe from 2 × 10⁻⁷ electron volt or so up. But at lower masses, it's clear. So these things, they get too big. One has to use other methods rather than microwave cavities. And we will discuss these things which come to the left, called abracadabra or dark matter radio and so on, and also these things which go to the right, like, for example, this Mad Max experiment and brass. So, but so in this middle, and this is a well motivated range of parameter range which is tested here. Of course, as I said, below 28 microelectron volts, so below that, it's only possible in a pre-inflationary scenario, and above that, both scenario can produce an Axon dark matter. But in this region also the initial vacuum angle has not been fine-tuned, so everything is very nice. But if you now suppose that, or you believe that the Axion is associated with the gut scale, then you should they would look at the wrong place. But okay, the parameter space is so huge. One has to initially have its own bed, so to say. Now let us see how one can go to higher masses. So to higher masses, it's no more good to the microwave cavities are losing their charm and the effectivity because the volume gets so small and so on. So there is an idea to use dish antennas instead. So what is the dish antenna based on? So again, of course, one is basing it. So all these or many of these dark matter detections, they are searching for Axon dark matter via its interaction with electromagnetism. So via this E.B interaction. Now, in this case, so one wants to use the fact that an oscillating Axon dark matter field in a background magnetic field, this carries a small electric field component. And so one idea which came us to mind was, if you place if you have a magnetized mirror in the Axion dark matter background, this will radiate photons. So if you have here a mirror which is magnetized, so parallel to this plane, then this mirror will radiate photons, and these photons you can somehow collect. You can suppose you have here a circular mirror, and then you can collect and all these generated photons into a detector. So I mean the generated power per unit of area is quite small. It's 10⁻⁻27 watt per meter squared for a typical GA gamma of 10⁻⁻14 GeV⁻⁻1. Let us see what this means. 10 to the minus 14 is around here. So for 10 to the minus 14, this is something which you would be like to be sensitive at this 28 at these 28 or 30 microelectron volt mass. So the power, the generated power, even if you have a 10 Tesla field, would be of the order of 10 to the minus 27 watt per meter squared. So what you can nowadays, what you can easily measure is maybe 10 to the minus 21 watt per meter squared. So this is 10 to minus 21 watt. So either you have a huge mirror. So you should have really a huge magnetized mirror in order to get it, or you have to somehow boost this. But we were first thinking of a big mirror, and in Hamburg, and Dieter Horns, he made up is presently setting up an Axion dark matter dish antenna experiment, which is called BRASS. So this is somehow the concept. You have a spherical reflector, which has a permanently magnetized surface for Axion photon conversion, and you have in the middle you have a receiver module, which is called a cold receiver and so on, and so essentially it goes like that. You have this permanent magnet. This permanent magnet will out of this magnet there come this electromagnetic wave or photons which go to this spherical reflector. All the light is concentrated here in the receiver module, and then you have seen, so to say, that the dark matter by photons, so to say, light made by dark matter. The broadband, and you want to use a broadband acquisition bandwidths and so on. But yeah, we will see. So what the projected sensitivity would be somehow in this range. It would not. So at the moment, in this first phase of BRASS, you would not really be able to probe the QCD axon, but an axion-like particle, so to say, with a higher photon coupling, could be probed by this experiment. And in particular, in the mass region, which is otherwise not tested by other experiments. Now, in order to go really deeper and to have a higher sensitivity, well, there has been the proposal of a boosted dish antenna, namely something of exploiting an open dielectric resonator. So the idea is to add a stack of dielectric disks with lambda half spacing, where lambda is the wavelength of the axion, so to say, the Compton wavelength, spacing in front of the mirror, all immersed in a magnetic field. And then if you have this lambda half spacing, then you have you get a constructive interference of the photon part of the wave function, and this resonantly produced photons, again, you detect with a receiver. Now, of course, I mean, if this, so you have to have the possibilities to in order to tune or to scan the frequencies, you have to be able to change the distance between these dielectric disks, and so this will be a complicated mechanical object. So this kind of idea has been taken by the MadMax experiment, which has been proposed to be built at DESY, but the original proposal was from the Max Planck Institute in Munich. So from 2007 to 2019, the conceptual design report was written and so on. Now, at the moment, a prototype is built at CERN at an available magnet, the so-called Morpurgo magnet, a smaller version of the final MADMAX experiment with only 1/10 of the area, and instead of 80 adjustable dielectric tests, only 20, and the magnetic field, which is only of order 2 Tesla instead of the proposed 10 Tesla, and so on. And with this prototype at the moment, or this is set up, and then data is taken, and if everything is fine there, then later on one is building the whole experiment, which could then start maybe in 2028 and go to 2038 at DESY. Now, MADMAX is projected to probe very deep into the Axion band in the mass range preferred by the post-inflationary Paget-Quinn symmetry breaking scenario. So this rather busy plot has again this Axion photon coupling versus the Axion mass. Here are the predictions of Axion models, and here in green, this is the projected sensitivity of MADMAX, and everything what is in high yellow is, so to say, the mass range favored by the post-inflationary scenario, and also this compared to this, the current limits by ADMX and CAP and so on. So this is a nice area where nobody else is fishing at the moment, and this prototype, but this, of course, this prototype experiment is not going really, will not go really deep into this region, because it's exploiting, because the cross section is not as high, or the volume is not as high, the magnetic field is not as high, and so on. Yes. And then there has been another proposal also going into it's a modified dish antenna proposal. It's again also some kind of boost dish antenna. One replaces the magnetized dish by an antiferromagnetic topological insulator. This sounds really crazy. Maybe it is, but the idea is somehow to use a feature from such topological insulators. Some of these antiferromagnetic topological insulators, they predict to feature axionic quasiparticles. So really, so longitudinal spin fluctuations coupled to E dot B. So it's really, it's something like a solid state axion, so to say. And in the presence of the magnetic field, the induced oscillating electric field associated with the dark matter axion field. So as I said, so I mean, in each oscillating axion dark matter field, there is an induced oscillating electric field, and this field, if you have this topological insulator in the magnetic field, this mixes with this axionic quasiparticle, and this can lead to a resonant conversion into photons. So so one would then have, so to say, this dark matter axion would at the end go out, would convert in this topological insulator into terahertz photons. And so the sensitivity of this kind of experiments, so the proposed experiment is called 2-rad, is digging at quite high masses, even beyond MADMAX, into the band of Axion dark matter models. So it's it's interesting how that such theories, that such experiments are also proposed. So I think again I stop here and ask for questions.
Okay, are there any questions from the students? Yes, in the meantime, I have a curiosity about one of the first experiment, the one with the cavity with microwaves.
Yeah.
Maybe you said, but I didn't get. Of course, you enter in the resonance with some width.
Yeah.
Right. So this width is of the order of what?
10 to the minus 6
electron volts.
Yeah.
Electron volt.
No, the relative width is 10 to the minus 6.
Ah, okay. Oh, so it's okay.
So it's really a very thin line. It's really very thin line. Okay, and therefore, so it's really, so normally, so you cannot even use, so to say, the same cavity for a huge range. You have to build
a cavity
cavities for different ranges, and then they tune these cavities by putting a rod in and so on, and screwing with this rod. So and then they measure, so to say, maybe a few minutes at one point, and then they go to the next, the next, the next, and then at some point it doesn't make sense with the same cavity, and then they have to replace it by a new one.
But in principle, I mean, you say microwave, you could go everywhere, but at some large frequency, you break the cavity because you enter inside. I mean, if the frequency is too high.
It's too high. This cavity is so small. I mean, then it's, and you want to use the lowest modes, which are very nicely separated from the others. And you can only use those modes which have an appreciable E field along the magnetic field of the direction of the magnetic field, so to say. Yeah, because you want to have E dot P maximal. Yeah.
Mm-hmm.
So so this is so the scanning speed is the crucial thing which you have to maximize the if somebody would tell you what the axion mass is, then you can immediately, so they are saying typically, if you tell us the axion mass, we see the dark matter axion within 1 day. But of course I should give them the axion mass to an accuracy of 10 to the minus 6. Yeah.
Okay. Questions from the students? Okay, it seems not. So you have for today.
I think I will stop here because otherwise, yeah.
You go because tomorrow there will be the last lecture, right?
Yeah, there will be the last lecture. Yes.
Okay.
And I will continue with experiments also then with experiments which are not looking for dark matter but rather directly for these things. And I will also give a bit an overview that with this that it has recently been found that with many of these detectors you could also search for high frequency gravitational waves, which is somehow a new development that you sometimes you can just recast the limits which we have taken for Axion. For Axions, you can, for the Axion photon coupling, you can translate into a limit on gravitational waves.
The gravitational wave, I mean, if I think about LIGO or Virgo, they were talking about 10 to the minus 18 meters.
Yeah.
Right?
Yeah, but they are not searching for displacement, but they're searching for induced electric or magnetic fields.
Oh, okay. So
it's something. It's again. So it's searching via electromagnetism, so to say, and not via space,
the space
contraction and so on.
Okay.
So which is quite interesting. So at some point maybe this Axion experiments, they will also
go in that direction.
go in that direction.
Mhm.
Okay, so if it's okay, then I will stop here.
Sure.
But I'm also sure free for further questions and so on. So I mean, it's not.
Any last questions? Seems no. Okay. Thanks a lot, Andreas.
Yeah, you're
See you
welcome.
tomorrow.
Yeah, see you tomorrow, Vincenzo. Cheers.
Cheers.